and the invitation to give a talk, and this is a great initiative, I think, so congratulations. Yeah, today I'm gonna present the work that I did indeed in the University of Barcelona. However, now I moved to Rome, to Sapienza University. I'm doing a postdoc there. But this is the work done in the group of Professor Pietro Tierno indeed in Barcelona during my PhD. Okay, so first of all, just let me share a couple of videos of what we'll see. These are, sorry, as the title says, colloidal spinners. These are both videos of the same particles, just spinning with a different frequency in the magnetic field. In the right, we see particles spinning faster, and in the left, spinning slower. We'll see the difference in the physics in these systems, and why this is a different phase separation than the one on the right. Okay, so just to give you a brief outline of what I'll talk, our system consists of spinning magnetic rotors that strongly interact via hydrodynamic interactions. I'll talk about why this is a key ingredient in our system and how these affect the different dynamics. These hydrodynamic interactions, we'll see that they impede coarsening in these magnetic systems and result in finite clusters whose size can be controlled by the field frequency. As I showed you now, just in this couple of videos, we'll see how you can twitch the frequency, and with that, you change the size of the clusters. Also, I'll briefly show how formation of large aggregates shows circulating edge currents, as has been seen previously in similar chiral fluids and systems. A brief introduction of things most of you, I'm sure you already know. There have been a lot of studies made on aggregates in active matter and in magnetic systems. This very cool work of Palacci in Science in 2013, where self-propelled particles assembled in these organized and living crystals where they broke and assembled again. Also, of course, the very well-known image of a school of fish, but this is kind of relevant, but because we have to remember that this can have analogs in nature. In our case, with magnetic particles, they are all aligned and they have these aligning interactions that you naively can see in nature in other systems. What else? Also, with magnetic systems, they have been shown aggregates in crystals of Janus colloids. In this case, again, it was ordered. It was also a rotating system. This is again a rotating field in the plane. Both these systems are rotating field in the plane. And also this Nature Physics published very recently with this very cool chiral fluids made up of thousands of magnetic particles, in which they saw this collective dynamics and this collective behavior of these fluids made of similar particles than we did. However, in this talk, I'm going to show you how if you twitch a bit the frequency of the spinning magnetic field, instead of having a large chiral fluid, you'll have finite size aggregates of particles. Okay, let's go into our work. This is the colloids we use. This we synthesize with using a well-known salt gel method, which is cool because it allows us to obtain large quantities of these particles, which is good for our study in this case. And also we have these very monodisperse systems, and with this ellipsoid micron-sized colloids. It's important to note that they're ferromagnetic, which means they have a permanent moment. And in this case, they have the permanent moment perpendicular to their long axis, which is a peculiarity of how this hematite crystallizes. In this case, we have our particles are 1.8 microns long axis and 1.3 short axis, just to give you an idea. And yeah, as I told you, this is how the permanent magnetic moment in the particle is oriented. So How do we assemble these aggregates? How is our system working? What we do is we apply a rotating magnetic field, circularly polarized in the sample plane. We're in a two-dimensional system. We let the particle sediment close to a glass plate, which plays an important ingredient in the physics in the system, as I'll show you later. And we apply this rotating field, and the particles follow this magnetic field and spin with the same frequency in the field of frequencies and in the range of frequencies and strength of magnetic field used. They spin with the same frequency, which means you can, by just changing the frequency of the magnetic field that you apply, you can change the spinning frequency of the particles. This also means that the particles will have hydrodynamic interactions. The faster, just briefly, you can think of it, if the faster they spin, the stronger the hydrodynamic interactions will be. However, they will, of course, experience attractive magnetic interactions between them. This is because there's an average attraction on plane. So you have if you average over a certain cycles, you have this average attraction between all of the particles, which leads to this formation of clusters, which has been seen before in the works that I showed you. First of all, what we do is we calibrate, we try to see how are the strength of these magnetic interactions, these average magnetic interactions. I'm just briefly going to show you a video of what this happens. This is the field that the two particles spinning with a magnetic field that of 3 milliteslas, and they end up they start rotating, following the field, and of course they end up collapsing because of these average attractive interactions that they experience. We measure this for different frequencies of the field with the same strength of the field. We see that in the end, there's always a dipolar attraction, but we see a bit of difference in the amplitudes in the oscillation for longer distances. The stronger the frequency, the higher these fluctuations. This is mainly because raising the frequency increases the spinning velocity of the particles, which increases the strength of the hydrodynamic interactions. However, the dipolar attractions remain unchanged. The same dependence happens. So that's the key to our system. We keep the magnetic interactions the same while increasing the strength of the hydrodynamic interactions. And I'll show you collectively what happens when you increase the strength of the hydrodynamic interactions. So, as I said, by varying the driving frequency, you have these different types behaviors. These are videos obtained after minutes or sometimes hours of, in these cases, these are more or less stationary states. The clusters don't grow anymore, as I'll show you in a graph in a couple of seconds. However, in this case, we see that as you've seen these two, the clusters keep merging until they form a very large aggregate. As you see, they keep merging. So these are snapshots of what the videos that I just showed you after a long times. So, and this graph shows this is an adimensional length divided by so the length, the characteristic length of the clusters divided by the particle radius. And this is time, scale time with frequency, so adimensional time. And we can clearly see that there's one case, low frequency, which means low hydrodynamic interactions and high magnetic interactions. We see that we observe this coarsening, the clusters keep growing and growing indefinitely, at least in the time window observed. However, already at 20 hertz of spinning frequency of both the particles and the magnetic field, we see that the clusters saturate at a certain size. As we increase the frequency of this driving field, we see that the cluster size decreases systematically, as you also can see in these different snapshots. Okay, and this is the stationary size of this, so the average value of this saturation, let's say. for different frequency. As I said, we see that it decreases with the frequency. And we observe a dependence that's very similar to 1 divided by the frequency. This is, we notice this because it's reminiscent of other different types of systems, dry, active matter with aligning interactions, for instance. However, these are not only, of course, they're not dry, the hydrodynamic interactions are at the core of this phenomenon. But also the clusters that we observe do not disassemble and assemble again. The clusters that are formed stay stable, at least again in the window of time observed experimentally, which is hours. And then we ask ourselves, are these truly characteristic stationary sizes? Because is this a matter of time that we are not doing the experiment long enough? We didn't think so, but to check, what we did, we performed several quenches. Well, so we suddenly changed the driving frequency. We went from 10 hertz, which is again the coarsening state in which it grows indefinitely, to then increasing where we observe these finite size clusters. So this is what happened. We observed that the clusters kept growing always in 10 hertz. However, when we switched the frequency to 20 hertz, we saw that the sizes rapidly decreased and saturated again in a stationary value. And then while changing again to 30 and 40, it decreased again and it saturated to this constant value. And what's more impressive is that if these are lines, these are not the lines of these values that I show you, but the ones from the previous graph. So the ones obtained naturally without changing frequency, the stationary state values. So we see that these indeed seem characteristic sizes depending on the frequency. And they are almost identical. So we can conclude that the frequency effectively controls the aggregate size in this scenario. Next, as I said, we analyzed a bit of the structure of these clusters that form of these large clusters. This is a video of one cluster already formed. As expected in these spinning systems, in these chiral systems, we have an edge current in which the particles surrounding move much faster than the ones in the middle, which almost, as you can see, maybe they don't move almost, and the ones on the edge are the ones that move faster. So we analyzed a bit quantitatively these physics in these systems. So here you have the trajectories in these three size clusters. We see that again there's a layer for all sizes. There's a layer in which the particles, these are the trajectories in which the particles move and keep spinning, and in the middle they almost don't move. It's you just see a bit of almost diffusion of the particle. So as I said, fast spinners, we see that they circulate around a slower compact particle region. If we plot this tangential velocity as a function of the radius, so this would be the velocity, this line here is this case as you see in the right, this would be the velocity of the particles on the edge of the radius. And you see this dependency, of course, again, it goes to almost zero in the middle, but as you lower the cluster size, you see that almost all of the particles move again because this edge layer constitutes the entire cluster. You can think of it as that. And also we note that for smaller clusters, the velocity in the edge is higher than for large clusters. This is expected because for larger clusters, there's larger magnetic interaction. So you can think of the particles that are moving around the cluster are more attracted towards their center and they have a lower velocity. We compare these experimental values with this equation, which also appeared in the Nature Physics paper. This is just considering the hydrodynamic equations of motion, considering the whole cluster as a continuum. And we can see that it follows a dependency as the expected dependency, and we obtain very reasonable, let's say, penetration depth, which is 5 microns. This is a few particle radius. Think of that the particle radius is around 1.5 microns. So it's very reasonable. And again, all of the results fit very well with the data. And finally, just let me show you a few simulations. These were done in collaboration with Demian Levis and Professor Ignacio Pagona Barraga. What they did a particle-based approach because it was important to understand, again, the hydrodynamic interactions in these systems. Their main ingredients, they just put rotations of particles at a fixed constant angular velocity, which is our case experimentally. They put that the particles have attractive interactions with a short range steric repulsion, which is again very similar to the real case. And of course, they introduced low Reynolds number hydrodynamics, and they also introduced with this hydrodynamics an interaction with the confining plane with the glass that we have next to the particles, which I'll show you now how that is important too. This is just a video of one of the simulations they did. As you can see, it's very similar to our experiments, and you see again this cluster formation, and the different colors are different velocities, so you'd see that the particles on the edge also move faster than the particles on the middle. Then they analyze a bit the results with the parameter of reduced frequency, which is, you can think of it as the ratio between the spinning rate and the potential, the attractive energy. So what they see is they study the growth of these clusters, and we see that for low lambda, we can think of it that attractions dominate, and they have so low frequency for us, so lower hydrodynamic interaction. They see again this infinite growing, let's say, and they continuously grow and condensate into this giant cluster. All of the particles condensate. However, again, with larger lambda, which means for us higher spinning frequency, means that the chiral flows dominate. And they do see this behavior of a frustrated growth of the clusters, and they see that it saturates at a certain value, as we've seen also experimentally. Also, they, since with simulations, that is to remove the wall and to tweak the distance from the particles from the wall is very easy to do, not as much experimentally. So what they did, they studied the dependence on the distance h of the particles from the bottom plane. So high h, almost very high one, which means almost particles in bulk, two-dimensional, but in bulk without any wall. We see that a large cluster emerges, and also that particles at its edge can move arbitrarily fast. This cluster grows infinitely. They did all of the simulations, all of the particles end up in the cluster, and the particles on the edge can move arbitrarily fast. However, with the same parameters, if they introduce a wall or they put it at a lower height, they see that the same system is breaking into smaller clusters. So the wall limits this fast rotation, and we can conclude that it's at the origin of this arrested growth of the aggregates, which is a very interesting result, I think. Also, this is the growth, for different age. So again, with high age, they see that they grow infinitely. I think you can see here that it looks like it saturates, but it's just because all of the particles in the simulation are in the same cluster. But with lowering age, you can see again finite clusters. So briefly to conclude, I showed you how a chiral active fluid made with an ensemble of magnetic spinning particles separates into finite clusters due to hydrodynamic interaction. And what's more, you can control the cluster size with a driving frequency at any time of the experiment, which is very useful, and this may provide strategies to control pattern formation in other active matter systems. And just finally, just a brief show of what I'm doing now. So all of that I showed you is my work at the PhD in the University of Barcelona, but as I said, I'm now in Sapienza University of Rome, working with bacteria, and I'll also shortly be introducing also magnetic particles, but for now I'm working with photokinetic bacteria, which I control with light. So I like to put these two images together because I like to think that I'm doing similar things again. Instead of controlling magnets with magnetic particles with magnetic fields, I'm controlling bacteria with light. So I think this is cool. So again, thank you for your attention and any questions that you might have.